So hi guys, hi, good afternoon. So use this. Please change your name, whatever this is. I'm giving you a one-time opportunity to change the name. Please change your name, whoever it is. So yeah. So hi, good afternoon, Hari Prasad, Priyanka. So hi, good afternoon, Hari Prasad. I'm fine. I'm doing good. So how are you? Hi, Anusha. Good afternoon. So, guys, please be quick, okay? And we have to complete this chapter. I mean, we have to be quick with content, okay? So, please let me know. So, I'm quickly launching the technical check. Please let me know if my voice is audible clearly and if my screen is visible clearly. And let me know if I need to be more louder, okay? If you feel my voice is very low, let me know at any time, okay? Come on, guys. Please join fast. Join fast. Yeah. So hi, Kriti Dev. Hi, Anusha. Bro. Yeah. So today we are going to start with again. We'll start fresh electricity. So we'll be discussing about the electric current. So the conductors, electric field in conductors, drift of electrons, and mobility of electrons in today's class. Okay. So hi, Adarsh. Good afternoon. So hope everyone is have come prepared. So guys, this is one of the best and interesting chapters you could see. I mean, we could learn. Okay. So this chapter is having highest weightage. This is very easy to learn. This is a chapter which is very easy to learn. At the same time, it's the highest scoring chapter. So you can score. You can expect at least of 3 to 4 questions, or at least 3 questions. Say one question on in resistor, one question on Kirchhoff's laws, and one question on potentiometer or meter gauge. So you could expect at least 3 questions from this chapter in your JEE mains. So 3 questions means it's directly 12 marks. Okay. So this chapter is very, very important. Please listen carefully to each and every point and let me know at any point if you have any doubts. Okay. So let's begin the chapter then. So before beginning, let me see if yes, okay, there are, I expect more students to arrive, guys. Please, we don't have much time to waste. So I request all of you to be on time, okay? So I'm going to end the poll now. So let's begin our journey. So yeah, in our previous class, we learned about current electricity. So you guys said what is current, what is electricity, and how they are different. So what is we learned about how the word current came. It was from the mechanics, which we got the term current. It was the water current, which we initially learned, right? So later on, say in the year 1747, okay, in the year 1747, there was this guy called Benjamin Franklin. How many of you know Benjamin Franklin? I hope most of you might know this guy, Benjamin Franklin. So this guy, what he did, he gave idea about current flow. So this guy is the one who gave idea of charges flowing. Okay, so this guy by convention, this one he gave convention. This guy gave that the electrons which we know are negative, are having a charge of minus, so negative charge. So before the discovery of electron, actually, J.J. Thomson, the renowned scientist J.J. Thomson gave the idea of electron or discovered electron in year 1897. Okay, so this guy discovered electron in 1897, but before that, in somewhere around 1747, Benjamin Franklin gave the idea that charges are flowing and electrons are having a negative charge. So approximately 150 plus 120, so nearly 270 years ago, this guy gave the convention that the electrons have a negative charge, and by convention we consider the positive charge flow as current. So this was done 270 years ago. So now we can't change anything. So yeah, that's one. So that's where I think it's somewhere near, right? So from today's date, it's 270 plus years ago. This was happened. This happened. So let's go with the brief introduction of how current happens or how conductors conduct electricity and what is the insignificance of conducting electricity. So in previous class we had studied this that the electric charges. So there are presence of electric charges in lightning. So in a battery when we click the switch, so what happens? There is a flow of current through the bulb or any device, any filament. That filament converts the electric charges or the flow of electric charges into light. Then we also saw these the nameplates of any electric device where they mention about the wattage required or the current or the voltage, etc. Power ratings and voltage ratings. So why do we write this? What is the significance of this? So why do we need all this? So we'll study all of these in detail in this chapter. Okay. So we had also seen that there exists a rating of 1.5 volts or power of 150 watts, etc. So what are these? Why are we using these? So we'll study in detail. So before that, we'll learn about what is current or what is current electricity. So the by definition, current electricity means the continuous flow of electrons in a circuit. Say if I have a circuit, what is a circuit, guys? What is a circuit? Now, the circuit means any closed path. Okay, circuit means any closed path. So if we have any closed path, say in this closed path, if I have an electron, if the electron is continuously moving, say if I have an electron, say most of you might have learnt about, and most of you might have played these car games where they call the circuit, right? The start point and finish point. Say if I have an electron which is moving from start point and ending at the again ending at the same start point. So if an electron continuously flow because of the presence of some force, say if there exists some force which is pushing the electron to move, or if there exists some force which is making the charges flow continuously in a closed path, then such path or such flow of current or such flow of charges is called as electric current. Okay, I hope all of you know got to know what is the definition of electric current. Yes. Next, we'll discuss about how electric current is existing in a conductor. Now, guys, what is a conductor? So tell me, what is a conductor? Before we discuss about electric current in conductor, what is a conductor? Please reply, guys. Guys, if you please be quick in reply. Yes, conductor. Yes, conductor is any device which allows, so which allows free flow of current or free flow of charges through it, right? So yeah, which can allow free flow of charges passing through it. So a conductor, say, what are the examples of conductor, guys? So I want some examples of conductor. Come on, give me. What are the examples of conductor you could give? YouTubers, please try to be active, guys. Please answer. Yeah. Yes, that is correct. So all metals. So all metals can be a good conductor. Yes. So example like, yeah, that is correct. That is okay, super. So there are some metals like copper, gold, silver, aluminum, so etc. Yes, even yeah, some non-metals. Say some non-metals also are good conductors like graphite, only graphite. So it's the carbon form. Okay. Okay, there are some non-metals which are good conductors, that is graphite. So the solid conductors, so these can be considered as solid conductors. The metals, all metals, copper, gold, silver, aluminum, etc. So why are they considered as superconductors? Why are they considered as conductors, guys? So why you think copper, gold, silver, aluminum, etc. are conductors? Why do you think they are conductors? Because each one of these examples, copper, gold, aluminum, and silver, each one of them have only one similar quantity. I mean, only one similar property. What is that property? Each of these have only one valence electron in their outermost orbital. You know, so the gold, the copper, the silver, the aluminum, all of these have at least one valence electrons in their outermost orbital, and these valence electrons. So if I have a conductor, say if I have any conductor, say there are n number of atoms, so each atom in their outermost orbital they have one free electron. Now what happens? Is this free electrons, is it easy to remove or is it difficult to remove? These electrons have very small amount of ionization and these are very easy to remove, right? So what happens at room temperature? Please tell me, at room temperature what happens to them? So is room temperature enough for them? Is room temperature enough for these valence electrons to come out of their outermost shell? Yes. So only at the room temperature, yes, these electrons at the room temperature, they are easy to, they can gain that energy, the energy from the room temperature, whatever the heat is available at the room, they can absorb that heat and can move out of this outermost shell easily. So each of them have highest number of valence electrons which are free to be moving. So they are free to move from one orbital to the other orbital of other atom. Hence, they have highest conductivity. So what happens here? They have highest conductivity. So what is conductivity? So we learn about them in detail. So apart these, are there any liquid metals, guys? Sorry, are there any liquid conductors? Do we have any liquid conductors? So we have conductors like metals and some of you said non-metals too. So like graphite is the only one which has property of conducting. Is are there any liquid conductors? Okay, yeah. So again we have mercury, right? Mercury is again a metal one. So mercury, guys, if you say mercury, mercury is again a liquid metal. Okay, it melts at room temperature, so it's liquid in room temperature. So we don't consider mercury as a liquid actually. It's again it becomes a solid or it is a metal. Is there any other things? Yes, correct, Dhanush. So we have something called as salt water. Yeah, salt water, acids, actually not all acids, some of them, like the polarized acids. I mean, polarized solvents like water in presence of salt. So this salt and water, they mix together to form what? They have ions, the positively charged and negatively charged. So they have positive and negatively charged ions. So what happens? These ions conduct electricity. Okay, these are the metals and non-metals which conduct electricity. Now, so we say conducting of electricity, electric current, etc. Now, what is electric current exactly? So, in today's class, we'll learn about what is electric current, how electric field exists inside a conductor. So, what is drift of electrons and the origin of resistivity. Then we'll also learn about mobility of electrons. Okay. So first we'll learn about the electric current. So what is an electric current? Suppose, say we have a conductor and we learned about the conductor. So the electric current is the measure of amount of electrical charges transferred per unit time. Say if we have a conductor, say I have a conductor, let me consider a copper conductor, okay? So let me consider a copper conductor. Now, if I can connect a potential to this, so what is necessary for this? I need a potential difference. So I need a potential difference. I'll write it as PD or I'll write it as V, voltage. Now, when I apply a voltage to this, now if I consider there exists some region, say if I have a small temporary pass-through slit, say I have small one of the smallest. Consider I have one small filter like this. So present here. Now what happens? So we know the metals, the conductors consist of n number of electrons, right? So we have many number of electrons inside a conductor. So let's consider those conductors. Okay. So we have a number of atoms present inside a in a conductor. Now these conductors have n number of electrons. How many number of atoms are there? Those many number of electrons will be present. Now when I connect a potential, what happens to this? Yes, when I connect a potential, what happens here? So what should happen here when I connect a conductor? Cool, guys. Thank you. So when I can, sorry, when I connect a battery to this conductor, what will happen? So we know this battery has a potential, positive plate and a negative plate, or a positively charged plate and a negatively charged plate, which gives. So what happens to all the electrons present here? So there are electrons present in this conductor. These electrons are being pulled. So these electrons are being attracted by these positive plates. Can I say that? The electrons are being attracted by these positive plates. So what happens? There are n number of electrons which are moving from this conductor towards the positive plate of the battery. So when they are moving, how many of them are passing through this filter? Say if I consider a small filter, how many of them are passing or a small region? Say if I consider a small region, and if I stand here and observe this, so how many electrons are passing through this region at given at small unit of time? Say for 1 second, how much amount of charges? Say here the charges are electrons, right? How many charges or how many electrons are passing through this small filter or small screen for 1 second? So that will be what? That will be, yes, yes, that will be the direction of, or that will be the current. Current means the electrical current is the measure of the amount of electrical charges per unit time. For 1 second of time, how many number of charges are moving? For 1 second of time, how many charges are moving in a given region? Say if I consider this as a region, how many electrons are passing through this region is called as current. So the electric current is given by I is equals to Q by T. Okay. So Hari Prasad, which metal shows highest electrical conductivity? So Hari Prasad, gold, silver, all of them shows same amount of conductivity. So we can say gold has the highest amount of conductivity. Okay. Yes, all electrons move in the same direction, Spargo. So yeah, electron starts flowing and all electrons move in the same direction. Yeah. Next. Yeah. Next we have the current. It represents the flow of electrons. So how do we represent current, electric current, in terms of physics or in terms of maths? Say we represent the electric current by the symbol I. Say if we have, okay. Now before going to that, let us see how it is in the conductor. Say what is current, guys? Now we understood that the current means the flow of charges, right? What is current? The flow of charges per unit time. Say we have n number of positive charges in a conductor and n number of negative charges also inside a conductor. Inside a conductor, say if you consider one small conductor, it will be having n number of positive charges and n number of negative charges. So when we connect a potential difference, both of these positive and negative charges tend to move. So always we have to consider the net charges. Okay, whenever we are going to consider the current, we are going to consider the net charges flowing through the conductor. So the total current or net current in forward direction is considered as the current in convention. Okay. So what we have here all if same direction, no resistance, that case is not possible. So some moves in opposite. Okay, Hariprasad will come to that discussion. Okay, please wait. Yeah. So the net current. So whenever we are considering the current direction or current, we'll always consider net current. What is meant by net current? So net current means the net charges. So what is the net charges? It's the total amount of positive charges and negative charges. So it's the summation of total amount of positive charges and negative charges flowing through a given conductor for that unit time. So we'll write I is equals to Q by T. From here, we could see that I is equals to Q by T. From here, we can say Q is nothing but total amount of positive charges, summation of total number of positive charges plus of, since we know the negative charge is minus, so plus q plus or q plus minus of q minus. So net charges would be the summation of total number of positive charges and negative charges, or the difference between the total positive charge and negative charge would be the net charge q. So the net current is nothing but net charge per unit time. So it's nothing but net charge flowing per unit time. Okay, this can be considered as your current. So this can be also mathematically said that by using limit. So whenever we use limit, what is it, guys? What are we considering here? So we are considering a small amount of charge flowing at a small instant of time. So current is also means that the small amount of charge flowing at small instant of time is called as current. So whenever we have very small quantity, we represent them with limit of that small quantity. So this limit of small quantity can also be represented using the differentiation. So whenever we are going to measure very small quantity of any physical quantity, we will be representing it with differentiation or d, right? So then we can write the current in terms of dq by dt. Then I will be equals to small amount of charges flowing for small instant of time. Okay, this is also the unit of current. This is also the expression for current. Then the SI unit of current is given by ampere. Okay, so this is the expression for ampere. Any doubts in this, guys? Yes, small amount of current dq is the small amount of current for small instant of time. Okay, so the current is nothing. So summarizing this slide, we can say that the current, electric current, is the measure of amount of electrical charges transferred per unit time, where the charge transferred is always the net charge. We consider the net charge. Okay, hope all of you have got this. Yes. Okay, so we'll, any doubts? Yes, cool. So we'll solve a problem based on this. Okay, so let us solve a problem based on this. Say I have a conductor of 2 mm long. Say a conductor of 2 mm long having a cross section of wire as isolated, and 20 coulomb of charge is determined to pass through it in 40 seconds. So what is given? I am given with, say I have a 2 mm long wire. So I have a 2 mm long wire. Now this 2 mm long wire, I have 2 mm. So this is big equivalent. Actually, it's very small. So I have a 2 mm long wire. Sorry, 2 mm is not that long. 2 mm, okay, 2 mm long wire. Cross section of a wire is 2 mm long cross section wire of is isolated, and 20 coulomb of charge is determined to pass through it in 40 seconds. So I have a 2 mm long wire, and in this wire I am having 20 coulombs of charge passing through it. So in a piece of wire, say if I consider a long piece of wire, in this I consider a 2 mm small slit. In the small slit, 20 coulombs of charges are passing in 40 seconds. Okay. So what is the current flowing through this? Yes. I'm going to launch a poll for this, guys. Please answer in the polls. And note that I'll be giving only 30 seconds. Yes, correct, guys. Cool. So 20 coulombs of charge flowing through 40 coulombs. Okay. So yeah, please try to answer without options. So there are no options, right? So we'll check the answer, guys. So please share your answers in the chat box. Please share your answers in the chat box. Okay, most of you say 0.5 amperes. Let's check the answer. So we know that I is equals to Q by T. So that is 20 coulombs per 40 seconds. That is 0.5 coulombs per second, or that is 0.5 amperes. Yes, correct, guys. So most of you have given me the right answer, and everyone, So Bhargav, Hariprasad, Krishmurti, correct answer. Because here Uday, Rakesh, Anushas, and Dhanush had given the right answer. Correct, guys. Okay, others, please try to answer. Okay. So let's check another concept test. So we'll have another question. Say, please read the question very carefully. I have 10 power 6 protons. See, okay. Hope most of you have got the previous question. Now, please come to the next question. I have 10 power 6 protons are moving in forward direction. So I have a conductor in which I have 10 power 6 protons. Protons, guys, what are protons? What are protons? Hope everyone know what's a proton. So the protons are nothing but the positively charged particles. Okay. So I have 10 power 6 positively charged particles moving in forward direction, and same number of electrons are moving in backward direction through a cross section of area A in time interval 10 milliseconds. So again, the time is given as 10 milliseconds. Find the current passing through the cross section. They're asking what is the current passing through this cross section. Say I have a cross section area A, and 10 power 6 protons are moving in this direction, and 10 power 6 electrons are moving in this direction. Now, passing through this cross section area A in 10 milliseconds. Now, how much is the current? So, take 30 seconds of time and please try to answer. Answer is not 0. Hari Prasad, no, check your answer. Bhargav, check your answer. Please note that the positive and negative charges are moving in opposite direction. Please use the formula I is equals to Q plus minus Q minus by T. Know that I is equals to Q by T, that is total amount of positive charges minus of total number of negative charges. So it's the difference of total positive charges and negative charges passing through a given region. Please check this. Dhanush, right? Anusha, check your answer. Dhanush, please check your answer. Dhanush, give a proper answer in terms of powers also. So your magnitude is correct, Dhanush. Please give the proper answer. Hari Prasad, Bhargav, others, please check your answer. Anusha, check your answer. Dhanush, yeah, your magnitude is correct. Please give the powers also. No, Hari Prasad. Yes, Bhargav, correct. Srishti, okay, correct. Srishti, 1.6, okay. No, Srishti, check with the powers again, please. Srishti, please check with the powers. Okay, so come on, guys, let's check. So we know that I is equals to Q by T, that is. So we know that one charge, say there are n number of protons and electrons. So one proton, say one proton is one positive charge and one electron is one negative charge. So 1 coulomb of proton, say I can say 1 coulomb of positive charge and 1 coulomb of negative charge. So how much is 1 coulomb of charge? So how much is one charge in coulomb? Sorry. How much is one charge or one positive charge and one negative charge in coulomb? So one charge in coulomb is 1.6 into 10 power minus 19, right? 1.6 into 10 power minus 19 coulombs. So similarly, one negative charge means that is 1.6 into 10 power minus 19, that is minus 1.6 into 10 power minus 19 coulombs. Now, if we add them together, how much we get? So 1.6 plus 1.6, how much is it? Yes, correct, Uday. Yes, that is 3.2 into 10 power minus 13 by 10 into 10 power minus 3 seconds. So these many amount of charges are flowing for given instant of time. Okay. So please note that we have to consider whenever they have given. So 10 power 6 protons, that is not only 10 power 6, we have to consider each the magnitude of charge also. While calculating, we have to consider the magnitude of charge also. Hope everyone have got this. So the current I would be 3.2 into 10 power minus 11 amperes. Everyone please make a note of it. So only Uday from YouTube have given me the answer. Others, please note this correction. Okay. Hope all of you have got this. Please reply with us if you have got this. Again, so what's happening? We know that current is the total amount of charges passing through this region. So in this region, there are n number of positive charges. So how many protons? 10 power 6 protons are moving in this direction, and 10 power plus 6 electrons are moving in opposite direction. Now, at this given region, say, okay, if I consider this region only, at this given region, how many charges are passing at a given time? So if I consider one region, one proton is passing here and one electron is passing here. So how many charges are passing at one instant of time? At one instant of time, how many electrons or how many charges are passing? Guys, please reply. At one instant of time, say if I have one positive charge and one negative charge passing this region, how many charges are passing? Two charges are passing, right? So it's not equals to 0. This from here, what I wanted to say is it's not equals to 0. Okay. So many of you got this as 0. We are not tallying the magnitudes. We are just considering the amount of charges crossing this given area. So they have given the area, amount of charges crossing this area is being determined. So we know that that is given by total number of positive charges minus of total number of negative charges crossing the area. So 1, so they have given 10 power 6 protons. So what is the magnitude of 1 proton? They had given 10 power 6 proton, right? What is the magnitude of 1 charge, 1 Q? Charge 1 proton, 1 plus Q is equals to, we know that 1 plus Q is 1.6 into 10 power minus 19 coulombs. Similarly, 1 minus Q, magnitude of 1 negative charge is 1.6 minus 1.6. Again, since this is negative, I'm considering it here, minus, I'm considering negative sign here. So that is minus 1.6 into 10 power minus 19 coulomb. So such, if one charge has this many amount of coulombs, how many does it have for 10 power 6? So multiply with 10 power 6. For 10 power 6 charges, there are 10 power 6 into 1.6 into 10 power minus 19 coulombs of charge. So if you try to simplify this, so if you try to plug in this value, this is the value of plus Q, this is the value of minus Q. So if you try to put the values in this equation, you will get the net Q as 2 times of Q, that is 2 into 1.6 into 10 power minus 19 into 10 power 6. So from here you would get that as 3.2 into 10 power minus 13 coulombs. In how many seconds are they going? In 10 milliseconds, that is 10 into 10 power minus 3 seconds. So on substituting all the values, we get the total current is given by 3.2 into 10 power minus 11 amperes. Hope everyone have got this. Guys, hope everyone have got this. So I'm going to erase this details. Shall I erase this? Is it required or shall I erase? So I'll erase it. Cool. Let it be. We'll go to next question. Okay, next concept. So we know there exists an electric current now, guys. Yeah. For any electric conductor, say we have any conductor, and for any electric field, so for any current to exist, we require some force, right? For any action, say for any action to happen, say if we have any conductor or if we have any body from Newton's law, we know that for a body to move, there should be a presence of force, right? We had learned in our 11th classes. A body stays to continue in the same state of rest if there is no external force applied, or a body which is moving in uniform motion continues to be in the same uniform motion until an external force is applied. We had learned this. Now, similarly, for an electron also, which is present inside an atom. So an electron which is present inside an atom, if that electron needs to move, there should be existence of some force, right? Yes or no? For an electron or a charge to move, there should be some force existing, right? Who is giving that force? Who is giving that force for that electron? So we'll learn that. So let us consider how an electric field. So we have known that the force for moving a charge. So if I have a charge, if this charge was supposed to move in a particular direction, what does I have to apply for making this charge move? Suppose I want to move this charge. Okay, what should I do, or how can I move this charge? Yes, by applying force. Which type of force? From where would I get that force? Guys, we learned it in our electrostatics, guys. Come on. Yes, we have a battery. That battery gives us an electric field. Yes, the battery gives us an electric field. Now, in the presence of electric field, what happens to this charge? In the presence of electric field, I have an electric field here. Say from a battery, I have generated an electric field. What happens to this charge now? This charge experiences a force. And what is the magnitude of that force, guys? F is equals to Q times of E. I hope everyone remembers this. F is equals to Q times of E. The electric field, how much amount of electric field I apply, same amount of force is being experienced by the charge and the charge starts to move. So similarly, what happens? Say in case of a conductor also, say if I have a conductor and I have n number of electrons, so I'm not drawing the atoms, guys. Instead, I'm showing only the electrons. Say if I have n number of electrons, and if I want to make these electrons move, what should I apply? Yes, I have to apply a potential difference or a battery. I have to connect a battery. Now, what does this battery do? This battery gives rise to a potential. It gives rise to a potential. This potential gives rise to a electric field. If you remember, V is equals to E by E dot dr is equals to V. If you have forgotten, please remember. Or E is equals to V by D. Hope you guys remember. So when I apply a potential difference, what's happening? I'm creating an electric field inside this conductor. That electric field, which is being present due to the battery, is making the electrons push, or is pushing the electrons, or is making the electrons move inside the conductor. So we'll learn how that happens inside the conductor. Okay. Guys, I hope you got the raw idea how an electron or how a battery makes the charges move. So we'll learn that in detail. So okay guys, so we know that, okay, before that we have one more problem. So we know I is equals to dq by dt, right? Hope most of you remember this problem. I is equals to dq by dt. So we have a problem based on this question. We have a problem based on this concept. Please solve this problem, then we'll go to that question. Okay. So if q is equals to 2t square plus 3, then find the current at t is equals to 2 seconds. So if I have an equation given as the charge q is equals to 2t square plus 3, q is equals to 2t square plus 3, then find the current at t is equals to 2 seconds. So guys, please try to solve this. We know I is equals to what? dq by dt. I hope most of you or all of you know how to differentiate. If anyone doesn't know how to differentiate, please let me know. Prakash. Others, please try to give the answer. So guys, you should be very quick with this. So just differentiate this, guys. What will I get on differentiation? So please just differentiate this. You know, I is equals to dq by dt. Differentiate this. What would I get? I is equals to dq by dt. That is, say if I have differentiation, Hariprasad, please do the differentiation. So it's differentiation of 2t square plus 3. So d by dt of 2t square plus 3. What happens? So if anyone doesn't know differentiation, dx by, say if I have dx power n by dx, then this differentiation is given by n into x power n minus 1. So n into x power n minus 1. This is the differentiation. So since I have the same denominator, if I have the same variable in the numerator and denominator, only then I can differentiate. So yes, the differentiation of any constant with respect to variable is 0 always. So here on differentiating we get, yes, 2t square. On differentiating we get 4t power 2 minus 1, that is 4t plus 0. If t is equals to 2 seconds, if I substitute the value of t, I'll get I is equals to 8 amperes. Okay, I is equals to 8 amperes is the right answer. Hope most of you have got this. Yes. Okay, guys, cool. So, any doubts in this, guys? Any doubts in this? Okay, no doubts. Cool. So let's go to electric field. So as we discussed about the electric field, so what was happening in case of electric field? So we discussed, right? So what's happening? So if we have a conductor and this conductor have n number of the electrons, when I connect a potential to this, what does this potential do? This potential or this potential difference which is applied creates an electric field. Inside this conductor, which makes the charges move. Okay, so we'll study in detail how does this happen. So how is it going to happen? Let's see. Okay, so let us consider a conductor. So let us consider a conductor of length L. So let L be the length of the conductor and let A be the area of cross section. So now if I connect a voltage source to this conductor, what will happen? Say let me consider a voltage source V, which is connected across this conductor. Now what happens in this case? When I connect a voltage source to this, what will happen? So how will it start to conduct? So when I say I have a voltage source V, when I connect this voltage source, what will happen? Yes, current flows through it. Which type of current? What is that current? So we know the current in general as I is equals to Q by T, right? I is equals to Q by T, which is this charge. So what happens in this case is, yes, there are a number of free electrons inside this conductor. Yes, correct. Super. So there are a number of free electrons in this conductor. When I connect a positive plate, what happens? All the electrons are being attracted to this positive plate, and all electrons starts to flow and come join this negative plate. Similarly, if there are n number of positive charges, say if there are n number of positive charges also available, what happens when I connect to this negative charge? So all positive charges would come and attract to this negative plate. This is one way of telling. Other way is what we generally say is the positive charges cannot move. That's what we have studied. So we have learned that the positive charges cannot move. So what we consider, this battery pumps up some electrons. So how many number of electrons are being pulled by this positive plate of battery? Same number of electrons will be flown. Yes, same number of electrons would be pumped or pushed by this electron given to this conductor to fill inside it. Yes, exactly. So no, how can it be possible, Dhanush? No, Dhanush, that's not. V is not direct. So now, if there exists, so whenever we connect a potential, so we know that from our previous chapter we had learned. So whenever we have connected a potential V, so we know that V is equals to E dot L, right? Okay. Yeah. So V is equals to E dot L or E dot R. So where L or R is the total distance, right? So there exists an electric field. Yes, correct. Cool. So V is equals to E dot L. From here, we know that the electric field, there exists an electric field in this conductor. When I connect a battery in this to this conductor, what happens? There exists an electric field inside the conductor. So this the battery sets up an electric field inside this conductor. Now this conductor starts to push. So what happens? So this conductor starts to push electrons or positive charges. Say, by convention, as I told in the beginning of the class, so there was this Benjamin Franklin guy. in 1747 said that electrons are negatively charged and are being pushed in the opposite direction always. So from then we took the convention as, so we have two types of current. So one is conventional current and other is convectional current. Dhanush, we'll discuss this in our Ohm's law, right? So please wait till then. Introducing Ohm's law now is not a good idea. We'll introduce Ohm's law at the time when it's required. Okay. Please wait till then. So we have some currents. Okay. So we consider. So there is something called as conventional current. So as I told earlier, so this guy, the Benjamin Franklin, in 1747, he gave that electrons are negative in charge. So my electrons move in opposite direction. Always motion of positive charges. The motion of positive charges inside the conductor is considered as the convention direction of conductor. So guys, please remember this very carefully. So the motion of positive charges, say all the electrons, the negative charges are being pushed in this direction, in the opposite direction to that of positive charges, and by convention, say thanks to Benjamin Franklin, we consider the conventional current as the direction of my actual current from the battery. So if I is equals to Q by T is the current, so we consider only the positive charges, flow of positive charges as the direction of current, or only the positive charges as current. Okay. So in actual, there will be presence of both positive charge flow and negative charge flow, but actually, truly speaking, only the electrons are being flown in the opposite direction. It makes us feel that all the positive charges are moving in the opposite direction. Okay. Cool. So the flow of positive charges is also called as the convention direction of current, and that is considered as the direction of current. So from now on, from here onwards, we won't use the word convention current. We'll just call it as current. Okay. So what do you mean by current, guys? The current generally means the flow of positive charges. Okay. Okay. Yes. Next. So the current flows in the direction of applied electric field or in the direction of flow of positive charges only. This is also called as the convention current. Well, inversely or conversely, so we know, or what do you mean by current? Current is the flow of opposite. So current flows opposite to the direction of negative charges, or what do we call current as? Current is the flow of, or current is considered, the direction of current is considered to as flow of positive charges, or current flows opposite to the direction of flow of negative charges. Okay. So this is the direction. So what is the direction of current? It's always the positive flow of positive charges is considered as direction of current. Okay. So there exists, so I said there exists an electric field. The electric field resistor, because of the presence of this battery, there exists an electric field inside the conductor, right? That is given by E is equals to V by D. So this is the same relation which we had learned in our previous class. So in our previous class, we had learned that there exists an electric field when, the potential, the relation between electric field and potential is given by V is equals to E dot dr. From here only we got this relation, V is equals to E is equals to V by D. Okay. So this is the same electric field which is applied. So moving forward, so what happens in, so we have a problem, guys, please listen to this problem. So when an electron is in a resistor flow from A to B, so I have a resistor and I have connected this resistor to the battery. So they have shown the direction of flow of, yes, E and I should be in the same direction. So we have given the direction of flow of electrons. Okay. At which direction is my current? So at which direction is my potential greater? Is in which direction is my potential greater? I'm launching the poll, guys. Please answer the poll. Please be quick. Don't take more than 20 seconds. Yes. So when an electron in a resistor flow from A to B, so guys, tell me from which direction to which direction does my current flow, convention current. Whenever I speak current, it's always I'm speaking about convention current. So from which direction to which direction does my current convention current flow? We had studied that the current flows from higher potential region to lower potential region, right? The current flows from higher potential region to lower potential region. So here the current means the convention current or the positive charge flow direction. So that positive charge flow direction is from higher potential region to lower potential region. Then here it's shown here that the electron is moving from this region to this region. So in which direction is my positive direction? Positive charges are moving. In which direction will my positive charge move? Correct, Chinmay. Correct, Hariprasad. So correct, Rashmudi. Yes, my positive charges will start to move from B to A. So this direction would be my convention current direction. So it's also given in the figure. Now, my current always flows from high potential to low potential or low potential to high potential. High to low or low to high. It's always from high to low. So what is the expression? So what is the answer, guys? Yes, most of you have given me the right answer. Option B. So my current flows from higher potential to lower potential. There will be a higher potential at this end and lower potential at this end. So potential will be greater at B than at A. Okay. My potential would be greater at B than at A. Thank you, guys. So next we have drift of electrons. Now we know the electrons. Say we have conductors. Again, we'll consider a conductor. Excuse me. Let us consider a conductor. Now this conductor has n number of free electrons in it, right? So these electrons are held to the outermost orbital of an atom, right? Guys, please let me please answer. So there are n number of atoms, and these atoms have one free electron at their outermost orbital, right? Now, as we discussed earlier, the room temperature is enough for these electrons to come out of their orbital, correct? So the room temperature is enough for them to come out of their orbital. Now, once they come out of their orbital, valence orbital, with what speed will they move? With what speed will they move? Will they stay in a place or will they move? These electrons, once they come out of their orbital, will they stay in a place or will they move? Yes, obviously they will move, right? So this movement of electrons, whatever this movement of electrons is also called as drift of electrons. So we'll be learning about drift of electrons and origin of resistivity. So let us consider a conductor. How this conductor, say in a conductor, how my electron starts to move. Yeah, these conductors moves with these electrons moves with some velocity. Inside a conductor, we have, so let us consider a conductor. Inside this conductor, let us consider an electron at this point. Say I have an electron at this point. Now, when I apply a potential or at the room temperature, it gains enough ionization energy so to move out of the outermost orbital. Now what happens? This electron, when it moves out of the outermost orbital, it starts to move in all random directions, right? It starts to move in all random directions. Now, say if I assume I have connected this to a battery. So when I connect this battery, there exists an electric field, right? In which direction will my electric field be, guys? So there exists an electric field, okay, whatever the direction. So what happens to this electron? This electron, yeah, there exists an electric field in this direction. Now, what happens to this electron? Yes, this electron will experience a force. How much force? Yes. So this electron will experience a force and starts to move in a random path. Okay, it will start to move in a random path. Now, when it's starting to move in a random path, it comes across with several atoms. What happens? There are several atoms present in this path. So it collides with each and every atom and it moves on in the against direction of electric field, right? So if this is the direction of my electric field, it moves against the direction of electric field, right? So since this is an electron, it moves against the direction of electric field, colliding with all other particles in its way. when it's moving from one end to other end, it experiences a small displacement. At this path of displacement, it collides with several other atoms. What happens now? So it experiences a force when it is for any atom to move or any material to move or any object to move, it should experience some force, right? So what is the force experienced by it? Now, what is this meant by? So whenever this electron moves inside a conductor, we call it as the drifting of electron. What do we call? We call it as the drifting of electrons. Okay. Now, if I consider this is the initial position of the electron and it moves to this some final position here, moves some final position here. Now, there is a displacement. Now, let us consider there exists a collision between any 2 points. Say, let me consider the collision between this point and this point. Okay. Now, the velocity of this ith electron. So, what can we write the velocity of this electron? So, the velocity of this ith electron at any given time is vi. So, this velocity, how much velocity is it moving with? So it will be moving with Vi is equal to 1 by n time of summation of all charges, that is Vi. So net motion of electron without the presence of electric field would be 0. Okay. Out of the conductor, it would be 0. Without the presence of external electric potential or potential difference, the net motion of electrons or the movement of electrons outside the conductor would be 0. But inside the conductor, there will be a zigzag movement of electron. Now, when I apply a potential, there exists a force on electron. Say the force F is given by F is equals to E dot E. Okay, where Q into E, we know that F is equals to Q times of E. Here, my charge Q is nothing but an electron. So I'll write minus E dot E. Now, can I apply Newton's second law? Because according to Newton's second law, we know that any object to move, there should be a presence of some force, right? That force from Newton's second law, What can we write this force as? What can we write this force as? Please, guys, reply in chat box. Reply, Madi, please. F is equals to, yes, m into a, right? Now, if we substitute the value of f, as ma, what do we get? So we get, on substituting value of ma is equals to minus e dot e, right? From here, what will be the acceleration experienced by an electron? Yes, correct way, thank you. So what will be the acceleration experienced by an electron? Acceleration experienced by electron is minus e dot e by m. So we have derived this expression several times in our 11th standard. Now we know from the kinematic equations. So we know the kinematic equation V is equals to U plus at. Since my electron experience a constant acceleration, a uniform acceleration or constant acceleration inside the conductor, I can apply a kinematic equation to find out what is its velocity. Okay, so if I consider V is equal to U plus at as an equation of kinematics, so if I substitute the value of V and take its average, so I'm considering the average velocity. Okay, so if I try to consider the average velocity, I get V average is equal to U average plus a times of T average. Again, guys, here T average is nothing but my tau. Okay, please remember my T average time is given by tau here. So I'll get the average velocity is equals to final average velocity equals to initial average velocity plus acceleration times time average. So this time average is tau. Now on substituting all the values, we get the initial average velocity of this charge or electron before applying my potential difference test. How much was my electron's velocity before applying voltage? So before room temperature also, it was 0, right? It was not able to come out of this conductor. But when I applied the voltage, what happened? This electron was experiencing a force and it tried to move out of this conductor. So yeah, initially the initial average velocity of this conductor is, this electron is 0. Then this average velocity experienced by this conductor is nothing but the drift velocity. It's nothing but the drift velocity. So this drift velocity is given by, so as I said earlier, drifting means the motion of these electrons is called as drifting, drift of electrons. So the velocity with which my electron moves inside a conductor is called as the drift velocity of that electron. Okay, so the drift velocity is given by expression is Vd is equals to minus E into E by M times of tau. So this is the expression for drift velocity. Okay, any doubts in this, guys? Hope everyone have got this drift velocity. So drift velocity of current. So inside, whenever I apply a potential to this conductor, what happens? This conductor pushes or gains, or there exists an electric field inside this conductor. This electric field provides the necessary force required by the electron to move. This necessary force required to move makes the electron move with certain velocity. That velocity with which the electron moves inside the conductor is called as the drift velocity. Hope everyone have got this, guys. Yes, next we'll go to the calculation. So yeah, this is the phenomenon of drift, and the velocity with which the electron moves inside the conductor is called as drift velocity. Now, can I write the expression of conductor? Can I write the expression of current in terms of drift velocity? Let us see how. So let us consider a conductor. Let L be the length of the conductor and A be the area of cross section of this conductor. Then let there be E amount of charge. So let there be N amount of charges which are moving inside, which are present inside the conductor, and each charge is moving with some velocity. Sir, will you say difference between velocity and diffusion velocity? Okay, drift velocity is the velocity with which an electron moves inside the conductor. Diffusion velocity is different. Say when it's the thing which happens in conduction. Okay, diffusion velocity is without that, in the absence of external electric field. Okay, Hari Prasad. Diffusion velocity of electrons is in the absence of electric field, how much it can move. That will be a diffusion velocity. Hari Prasad, hope I have answered your doubt. So let's come back here. So for the derivation of current using the expression of drift velocity. So we have considered a conductor of length L, area of cross section A, and let E be the charge on each of the electron moving with velocity. Say each electron is moving with certain velocity. This velocity is called as the drift velocity. Now let there be n number of free electrons per unit volume of the conductor. Then the current, you know that the current can be given as I is equals to Q by T. The current can be given as I is equals to Q by T. This charge. So how can I write my charge? So I can write my charge. The charge, total charge enclosed in this given volume of conductor is, say, charge in given. So net charge, Q net Q in given volume of conductor is given by, say I have the total volume of conductor is A into L times n number of electrons exist inside, and the charge on each electron is E. Then Q net is nothing but total volume of conductor multiplied with number of electrons multiplied with charge on electron. So I is equals to Q by T. On substituting this value of Q net, so I'll get I is equals to NALE by T. So again, guys, what is the basic definition of velocity? Velocity is nothing but total displacement upon time, right? So what is the net displacement of one electron inside this conductor? So the net displacement of one electron inside this conductor will be the total length, right? So the length upon time taken will be considered as my velocity. So for an electron which is moving with velocity, we consider that as a drift velocity. Then I can replace this Vd or L by T by a small term, that is Vd. So from here I can derive an expression for electric current, that is I is equals to N E A Vd, where the total current flowing through a given volume of conductor is given by I is equals to N E A Vd, where Vd is the drift velocity of the conductor. Okay. Hope all of you have got this. So next we have to derive an expression for current density. Say let us consider, so what is the current density? Whenever we have the volume condition, we have to define the density too. So what happens here? Let us consider a conductor of area of cross section A, that I be the current flowing through this. Then the current density is given by J. Okay, current density is given by J. J is equals to I by A, where I is the total current and A is the area of cross section of this conductor. Now, we know that from previous expression, I is given by I is equals to NEA VD. On substituting this value, what happens? My A and A in the numerator and denominator cancels. I get the expression for current density J as J is equals to NEVD. Now we know that VD from previous expression, we know that VD is minus or E into E. You consider only the magnitude of VD. So just so we'll consider the magnitude of VD. So VD is equals to E into E, total charge on electron into E by M times of tau. So on substituting the value of ED, we get the J, current density J is equals to NE, okay, this should be small j. So yeah, the J vector, so it should be a J vector, okay. So J vector is N into E times of E by M times of tau. So on substituting the value, we get J is equal to NE squared tau by M times of electric field. Okay. So what is my NE squared tau by M? You know, the NE squared tau by M is a constant and it's called as the conductivity of my conductor. So I can explain. So yes, sir, Professor, we'll discuss that. So the conductivity of any conductor, is given by the number of electrons. So the conductivity depends only on the time factor. If more number of electrons are passing at the small interval of time, then the conductivity is more. So here, this constant which we get is called as the conductivity of the conductor. Is given by sigma, that is equals to NE squared tau by M. Okay. Now, is there any other term? So whenever we have conductivity, we can define one more. So okay, we can write the expression for current density as J is equal to sigma times of P. We can write we can write this expression as J is equal to sigma times of P. Now, can I introduce a new term that is called as the resistivity? Say, if I have conductivity means how much my conductor can give the electrons, how much my conductor allows the flow of electrons to pass through it, allows the free flow of electrons is called as conductivity. Then the inverse of conductivity, say if I take the inverse of this, so if I take the inverse of conductivity, then I'll get a new term that is resistivity. Resistivity means how much, so I'll get a new term, resistivity. What is resistivity, guys? So we know conductivity. What is conductivity? How much the conductor allows free flow of electrons, right? Charges is called conductivity. Similarly, resistivity means how much it opposes, how much opposition for free flow. So how much of opposition we get for free flow of electrons is given by resistivity. It's the inverse of conductivity. So where rho is called as the resistivity. We'll learn about resistivity in detail. Okay, resistivity is nothing but inverse of conductivity. Yes, exactly. So we'll learn more about resistivity after Ohm's law. Now we'll learn about the mobility of electrons. Okay, the last topic for before that we'll solve one question, guys. Please take this question. Please check this question. If 1 ampere of current, is flowing through a copper wire of 2 millimeter square cross section. So area of cross section is given. A is equals to 2 millimeter square. Current I is 1 ampere. And yeah, so this is given. Now, what is the drift velocity? Vd is equals to what? Now to find what is the drift velocity. So we know I is equals to NEAVD. What are the and also they have given one more data for if number of free electrons in 1 centimeter cube of copper. So in 1 centimeter cube of copper, number of electrons, n is equals to 8.5 into 10 power 22. Okay, per centimeter cube. So this is per centimeter cube. What is the amount in meter cube, guys? What is the answer in meter cube? What is its value in meter cube? N in meter cube. Please reply your answers in chat box. Guys, if 1 centimeter cube has 8.5 into 10 power 22 number of electrons, then how many electrons, how many free electrons are present in 1 meter cube? So if you know this, you could apply this equation I is equals to NEABD to find what is your BD. Please try to solve this. Guys, I'm giving you 30 seconds of time to solve. Okay, take 1 minute of time to solve this. And I need the answer. Come on, guys, try to solve this. You should be very quick, guys. So there might be a probability that your JEE mains exam would be conducted on this February. So before that, we have to complete the syllabus. Please try to push yourself so that we should complete the syllabus at any cost, like before your exam starts, right? So if we complete the syllabus, it would be very easy for us since all of these concepts are already taught in your CBSE. Hope this lesson is completely taught, right? Okay, please try to solve this, guys. Yes, yeah. So let's try to solve. Okay, let's try to solve. I'm going to erase all the given data because in fact space. Yes, guys, come on, try to solve. Try to answer, guys. Please try to answer. So we know that I is equals to NEA VD. From here we can write VD is equals to I by NEA. Okay. So we have a conductor of area of cross section 2 millimeter square. That is 2 into 10 power minus 3. So how much is this? This is nothing but 2 into 10 power minus 3 whole square. From here I get 2 into 10 power minus 6 meter square. Similarly, for 1 centimeter, say the current flowing through this conductor is 1 ampere, right? The current flowing through this conductor is 1 ampere. Then how much amount of, for 1 ampere of current, so how many number of free electrons are there in 1 centimeter cube of copper? Say free electrons in 1 centimeter cube of copper is 8.5 into 10 power 22. Then how much in millimeters? If I try to convert in millimeters, I have to just multiply with 10 power plus 6. Okay, guys, please note that it's 10 power. So it's 10 power minus 2 whole cube. So that is 10 power minus 6. Sorry, this should be minus 6. 10 power minus 6. From here, 22 minus 6. How much is it? So in 1 meter cube, I would get. So yeah, n should be 8.5 only into 10 power 22 minus 6, guys. Please note that there is a small correction here. So 10 centi is 10 power minus 2. 10 power minus 2 whole cube is 10 power minus 6. So this should be 10 power 22 into 10 power minus 6. That is, yes, 10 power 22 into 10 power minus 6. 2, 4. Okay, 10 power plus 16. Yes, who had given me? Adarsh had given me this answer. Cool. Super Adarsh. So Adarsh, yeah, this is my n value, and please try to find my BD value, guys. If this is my n value, please try to find my BD value. Please make connection. This is 10 power minus 16. Sorry, plus 16. So it's not 28 plus 16. So try to find out my BD value. So I'll try to put options from next class for you guys. So it would be very easy for me to calculate them when take the answers. But guys, please be very quick with your answers. So please come prepared and please try to answer fast. So VD is equals to 1 by 8.5 into 10 power minus 16, so plus 16. So this is 16 into 1.6 into 10 power minus 19 into 2 into 10 power minus 6. So on simplifying, we will get Vd is 0.036 into 10 power minus 3 meters per second. Okay, guys. So this will be my drift velocity. This will be the value of drift velocity, that is 0.0367 millimeter per second. Okay. Yes, guys. So last topic of today's class is mobility of electrons. Say we know that the mobility of electrons. Mobility of electrons is the drift velocity per unit electric field. Okay. So what do you mean by mobility of electrons? Its mobility of electrons means, say in a conductor. Say I know I have a conductor. Now there are a number of free electrons. These free electrons, whenever I apply a potential, say whenever I apply a potential, there exists an electric field, right? There exists an electric field in this direction. Now, yeah, from positive to negative, right? So with this, in which direction will my electron flow, guys? In which direction will my electron flow? From left to right or right to left? From your screens, left to right or right to left? Please reply. Is it from left to right or right to left? Say electric field is in this direction. When I apply a potential, yes, it is. Electron, guys, movement of electron, not positive charge. I'm asking movement of electron. Electrons always flow opposite to the direction of electric field, right? Right. So my electron moves from left to right. Okay. Correct. So these electrons, how much of electrons move? So mobility, and you know what is mobility? Mobility is defined as the magnitude. How much of these electrons move with drift velocity Vd? So how much of these electrons move with drift velocity Vd per unit electric field? For every value of for for every single unit of electric field, how much, yeah, how much will be the velocity? So how much would be the mobility of this electron? So the mobility is given by, mobility is Vd by E. So we have an expression. So mobility is given as, mobility of electron is defined as the magnitude of drift velocity per unit electric field, and mobility is given by mu. It's defined by the Greek alphabet mu. Okay, so mu is equals to Vd by E, where mu is Vd upon E. So we know that Vd is equals to E into E by m times of tau. So we have again considered only the magnitude of Vd. So that is E into E by m into tau into 1 by E. So from here we can cancel my electric fields term. E and E gets cancelled. So you know that. So I don't have to represent that again. So my mu, mobility of electrons, is given by E into tau by m. So E into tau by m, this is my mobility of electron. So mobility is a scalar quantity. Okay, it's a scalar quantity. It's not having any direction. It only shows only the magnitude of how much electrons are moving for given electric field. Say mobility and then what is mobility? Mobility is just giving how much electrons are moving in a free, with velocity Vd in the presence of electric field. For unit electric field, how many, for every value of electric field, how many electrons are being moved? Okay, this is mobility of electrons. And mobility does not depend on electric field. See again, the mobility of electrons, is it depending on electric field? Mobility of electrons doesn't depend on electric field. But what does it depend on then? Electric field, but depends on what? Average time. Okay. Okay, this only depends on material properties. It only depends on material property. If my conductor is closely packed, I hope most of you remember, guys, this from your 10th standard. I hope most of you remember how are solids formed, how are liquid formed, how are gases formed. Hope this is remembered by you. So, say in solids, atoms are closely packed or loosely packed. Guys, please tell me. In my solids, what my electrons or atoms filled? Are they closely packed? or loosely packed. So in liquids we have, so in solids the atoms are closely packed. In liquids the atoms are loosely packed. In gases, I don't know, they are not packed at all. Very, very loosely packed. Hope this you guys remember na from your 10th standard में ऐसा ही पढ़ाया था. I hope. So what happens in case of solid? So say if I have any atom similar to that of solid, if the atoms are closely packed, then what happens? So how much space would I get for my electron to move? How much space will my electron get to move? How much space would my electron get to move? Very less space, right? If one electron takes if an electron takes very less time to go to next orbital. Say when the atoms are closely packed, the electrons take very less time to move from one orbital to other orbital, right? So if an electron takes very less time to move from one orbital to other orbital, we can say that the mobility of the electron is very less. Okay, we can say the mobility of electron is very less. Okay, here mobility is given by mu is equal to E tau by m, where E is the electron, charge on electron, m is the mass on electron. Then mobility is directly proportional to tau, which means if an electron takes very less time to go to next orbital or for next collision, for one collision to other collision, if there is very less time required, then mobility of electron is said to be very low. Okay, if time taken for electron to collide another atom is less. What can I say about the mobility, guys? Please reply. What can I say about the mobility? If time taken, tau represents the time taken, right? So I'll write time taken. Another atom. So time taken by an electron to collide another atom is less, which means tau is less. What happens to my mobility? Mobility will also be less. If my atoms are loosely packed, okay, what happens? The time taken by an atom to hit the next atom is more, right? What can you say about mobility here? Mobility will be also more. Okay, so my mobility is always proportional to time. Check scalar quantity. So this, this is first part of your this is the first part of your current electricity. In today's class, we discussed about conductors, electric field in conductors, drift of electrons, drift velocity of electrons, and mobility of electrons. Okay, so and we also solved many problems. So I'll just erase this and rewrite that. Okay, mobility of electrons depends on. Yep. Okay, so that's all for today's, guys. Please come prepared for tomorrow's class. We'll discuss more on. Next class would be on Ohm's law. Okay, please come prepared with Ohm's law. We'll discuss about problems on Ohm's law, and we'll also discuss on how to solve. Okay, we'll discuss about how the many short circuits on how to solve Ohm's law. Okay, problems on Ohm's law. How can we solve those? And yeah, we'll go with that. Okay, guys. So yeah, as I was telling, mobility of electrons depends on. Mobility depends. I'll write those. So the mobility depends only on material property. Okay, so this is what Okay, guys, then we'll meet again on tomorrow's class where we discuss about Ohm's law, and also we'll discuss about several problems. We'll also discuss how to say if we start with Kirchhoff's law, we can discuss about the shortcut techniques required by the Kirchhoff's law. So which are the shortcut techniques we have? So I can explain you some shortcut techniques to solve many problems in short duration of time. Okay. Yeah. We'll discuss about Ohm's law and Kirchhoff's law tomorrow. Please come prepared. Okay. Guys, yeah, again, I need to say one thing. So we have very less time and we have to be bit quick. Please try to respond quickly and try to be on time. Okay. So from tomorrow's class, please be on time. If possible, please be early by 5 minutes so that we can start our class early and we can discuss much more. Okay. Okay, guys. Any doubts? You could ask me. You could let me know if you have any doubts. Please let me know if you have any doubts. Okay, guys, cool. Thanks for your feedback, and we'll meet again on tomorrow's class. Bye. Then bye, bye, guys.